So thanks everyone for showing up on Tuesday, 02222022, which is also a Tuesday. And this is the second ever distributed systems reading group, so that also works out, more twos. This is a much easier paper, I think, than last time. So this is not 100 proofs. This is one observed behavior, I guess. 7 pages instead of 20 something last time. So yeah, and then hopefully I was hoping that the first one would kind of give like a good basis, and then we could do something a little bit more fun. So this is the more fun, possibly more relatable one. I gave the overview last time. Would anybody like to give a summary?
Yeah, I'm happy to.
Great.
Yeah, so metastable failures in distributed systems. I'm not positive, but I believe this paper is mostly out of observed behavior at Facebook. The main author, Nathan Bronson, spent time at Facebook before moving to Rockset. And
Spent
this
time, did time.
Did time.
Yeah.
Hopefully is atoning for that time. And this paper is really meant to categorize a number of failures that they saw at Facebook that like Brooke said a moment ago, were all these black swan events where there's nothing that predicted that they could happen, and they didn't seem to fit into any of the existing buckets for how they were thinking about and categorizing failures in the past. So after reviewing a lot of these failures, they came up with this way of thinking about them that they called metastable failures, which I think is best described by this state machine on the first page. But the idea is that you have both a trigger and a sustaining effect, where at some point an otherwise healthy system moves into what's known as the vulnerable state as load increases. And while it's in this vulnerable state, the system still appears to be healthy. However, it is only in this state that there's a trigger that can cause the vulnerable system to enter a metastable state, which is where there's decreased load, decreased good put, which I'm sure we'll talk about later, and so on. And there's some element of this metastable state that induces what they call the sustaining effect, which is basically a byproduct of this state that causes the state to continue existing until some sort of drastic action is taken to correct it, whether that's rebooting the system entirely, or changing like scheduler or caching policies, or like flushing all of the work queues and so on. But really the key thing that they are observing with these failures is that once the system enters the metastable state, it's not going to recover on its own unless there's a like hugely debilitating cascading failure or some sort of drastic corrective action taken. And to me, at least, the key point of these failures that they're talking about is that they happen through the interaction of this trigger and the sustaining effect, which each on their own, viewed independently, may not appear to be serious bugs or even issues with the system. It's only when the two kind of collide in the way that they talk about here that you start to see things fall over. I think that covers the gist of it. But then the rest of the paper goes through a couple of examples that they saw at Facebook, possibly elsewhere, and what they did to address those problems. So I don't know if anyone else wants to jump in from here.
Oh, one thing that they did that I thought was neat and made me curious if there were other equivalencies is when they were talking about, so the first example is talking about like just like request retries can do like query amplification, and like because your throughput is lowered, like that causes a feedback loop. But then like in the second example where they talk about the if your like cache goes away, suddenly you cannot handle as much load, and the increased load like acts as the feedback loop, and you still get a query amplification effect. And I thought the like equivalence there was neat, where it's like the cause of the query amplification was different, but it's still like boiled down to query amplification in the end. And I think they even call that out in the like in the conclusion. They talk about what was it? One of the like common patterns was work amplification. Yeah, in the discussion and research question section, the like work amplification was a unifying theme across this. And one thing I was wondering this is like totally just a wondering out loud sort of thing, was like, are there other ways to cause this sort of like metastable failure issue without doing work amplification, but still having some sort of feedback loop like that? I couldn't think of anything off the top of my head, but I also wasn't like, I'm not architecting giant distributed systems lately.
So I actually don't think you need a giant distributed system to have this. I've seen this in Elixir, where it's like, just let it fail and then it'll restart. It's like, but they're all failing, they're all restarting, and they're redoing all of this work, and they're redoing all of that work a bunch of times, and each of those calls out to several other systems that when this one goes down, that one's still going, and it can't call back, and so like you're stuck in this state, and it just goes, well, I'm actually out of PIDs, so I'm going to crash now, right? So it can happen kind of anywhere. Facebook obviously just does massive scales. So you probably see this like more frequently. I thought it was really interesting the second case that they gave, where it was like, and now the cache is down, and now your total system capability has dropped. So it's as if you were at a higher load, because you can't talk out to these things. I think they were saying specifically with look-aside caches as opposed to inline, that you'd have this a lot more. Because the timing even could be, well, we're not putting things in cache, though we think it's in cache, right? With the ordering.
Yeah.
Yeah, I actually had that exact experience years ago with the Drupal site that its homepage took longer to build than the cache expiry. So basically, if they ever flushed their cache, the site would go down. So yeah, we had to have basically an out of band cache filler. Because basically if that cache ever got cleared unexpectedly, I don't remember if it was Redis or Memcache, but whatever cache they were using, if that got cleared, restarted, whatever, they couldn't fill it again fast enough. So the whole site would just go down for exactly this reason, right? Like it would just get caught in this loop. It's trying to refresh the cache. There's nothing in the cache, so all of the requests are going through straight to the web servers, and ultimately it was the database that was the bottleneck. So yeah, it was a very I don't know, a lot of head nodding in this paper. I was like, oh yeah, that's a thing I've experienced. I know exactly what this is like. And you kind of, when it's happening, you don't have nice courses of action, right? Like stuff is going down. It's just going to keep piling up, and the backlog's just going to continue until you take more drastic measures to reduce the, in this case, the web traffic. So. I had a similar question around are there other kinds of things? Because again, in my experience, it's the workload, right? That compounds, that creates stuff like this. But I too couldn't think of any other ways to end up in these feedback loops.
I'm thinking that maybe the example from section 2.4 might be, or at least I find it hard to see the work amplification in there. So I think the idea is in the 2.4 section, you have a database cluster as well as a cache cluster, and they're connected over many links. But for some weird reason, which is dependent on some implementation detail of both the database cluster as well as the cache cluster, it gravitates, the link that is chosen between the two clusters gravitates towards the one that's used the most. And so you end up in a situation where in the end, in the failing state, everyone uses this one link, and you have a very, very slow connection between the database cluster and the cache cluster. And I don't quite see how, is that work amplification? I mean, maybe I'm not that familiar with work amplification myself.
I read it as such because it's amplifying the work of that link, right? And it's flooding that that particular link so that it's basically
Yeah.
unusable.
Yeah, it seemed like equivalent in the same way that the cache going down was equivalent to work amplification. It was as though you had just unplugged, like, or consumed all of the bandwidth of the links or whatever in the same way. And like, even though you were only doing 1/10 of that work, you were using 10 times, effectively using or equivalently using or whatever, 10 times the amount by not taking advantage of the other 9 links.
Yeah,
So,
actually, you know, that's interesting, right? Because they do say it's all some variation of work amplification, but this isn't really amplified. This is just like imbalanced, right? So it might be a weakness of the paper. Yeah.
Possibly.
yeah, it's like you could redefine work amplification, or at least my previous definition of work. You could redefine as like the quotient between available resources and work.
Yeah.
And if you have this quotient and you throw away lots of resources because you have some bugs in your code or your cache falls away, then that amplifies this quotient.
I think the quotient is a good way of thinking about it. To me, work amplification feels like a little bit of a misnomer. Later on in the paper, they talk about the difference between what they call hidden capacity and advertised capacity, where hidden capacity is basically how much load a service can handle, basically how much load a service can handle when it is in one of these metastable states, that like breakpoint where it's able to recover if the load drops below that. Whereas advertised capacity is the capacity of the service that basically the capacity that it looks like it can handle, because until that trigger effect happens, everything seems to be working properly. And in a lot of these cases, including that link imbalance one, what's happening here is they have different measures in place, whether that is load balancing or caching or retries and so on, that are actually meant to increase the availability or the efficiency or the resilience of the system. But they do that by increasing the advertised capacity by some factor of the hidden capacity. So then where these failures happen is when any of those measures fall down, and then, like Philip said, that quotient between the advertised capacity and the hidden capacity all ends up kind of like hitting you at once, like a tsunami.
Yeah. I thought the important thing
Yeah.
in that is in the, if you're within your hidden capacity, removing the trigger sets you back to like a working state. Whereas once you cross that hidden capacity, removing the trigger doesn't actually, that's the other thing that would like ring really true in this paper for me, is that, yeah, you get in these states where removing the trigger doesn't fix it, right? Like it's too late. you're in this feedback loop, and you need to address what they call the root cause, as opposed to just removing the trigger.
I wish, oh, sorry.
Do hidden capacity and advertised capacity correspond directly to stable and vulnerable? Like, is hidden capacity like the capacity when a system is in a stable state, and advertised is well, I guess maybe both stable and vulnerable? Like, how do those relate?
They define hidden capacity as the boundary between the stable and the vulnerable states.
Yeah.
Okay.
I kind of wish that they had gone into a little bit more detail about the image of the metastable states from physics, because I had to go and look it up separately, right? Did anybody else do this? Somebody want to give a description?
I didn't even know that there was something like that.
Right. So
they mentioned it briefly, but I didn't.
Yeah, it's like really quickly, like, from physics, moving on, right? It's like, well, we're not physicists, you know. So essentially, the idea is you'll have energy in a system, and you'll have fallen down. You're trying to get as low as possible, and you've fallen down into a local minimum, and then you'll actually need more energy to go back up before you can fall back down completely. So this is almost like, you know, when you have electron orbitals, you have to actually add, you know, you have to actually bump out of your orbital to actually fall down one more level, things like that, right? So the idea here with the metastable state is you're in this non-ideal state, but you actually need to do a massive corrective action to get back down to where you want to be.
I like that imagery.
Yeah. So yeah, I kind of wish that they had put that in, because it really explains, I think, better than this one, which is a more like, this is a more active diagram of you know, the cycle in the system, right? but they put it in the title and they never really explained it.
Going back to the link imbalance example, I don't know that it would meet all of your definition of one of these failures that doesn't fall out of work amplification. But I think there's a closely related failure that you see with like hash partitioning, which is a common technique for load balancing. You hash a key to determine which shard it goes to. And if you're not careful when you do this, so one of the main goals here is that like hash functions are uniformly distributed. So the keys will hopefully be uniformly distributed among the shards. But one of the failures that sometimes happens here is that if one of those shards goes down, you will kind of fail over the keys to the next best shard within the ring. And then that can cause a cascading failure, where if there's enough load for one shard to go down, then the next one will go down, and then everything starts getting funneled into the remaining ones. And you end up with, I guess that would probably be a sustaining effect that keeps you in this state until you stop incoming work from coming in. So I don't know if that's work amplification, but it's another example of that sort of imbalance.
Yeah, I wonder, is there a distinction here between a cascading failure and a metastable failure? Because I think the metastable failure stays up. If we're going to cascade through, that's going to take all of the nodes down, and then we're in a clean state, right? And we can start back up again, hopefully. So where's the division, I guess?
It feels like a cascading failure like that is like one of the exit points from the sort of like metastable failure state. And so, like, for example, if you also have like your automated infrastructure stuff keeps bringing the shards back up, now you're in an you're in an infinite loop where every shard is getting 3 shards of queries and then going down immediately, rinse and repeat or whatever. But with just the cascading failure, that's like if everything eventually goes down, that feels like it was in a metastable failure state for a little bit, and then it managed to like build up enough momentum to get over the hump and like take everything down and start it up again. At the very least, they seem like related. Definitely.
I wonder what everyone's thoughts on the actual best way to solve metastable failures or prevent metastable failures in the future are. Like unknown metastable failures is what I'm trying to get at. So I think there's like, the paper describes, in my mind, 2 distinct ways of dealing with it. One is you try to test these systems in the real world with either faked loads, or you have a way of like splitting your production into 2 systems, and you like gradually increase the partition of that one system experiences of all of the load to test like a new version, I guess, or something. And the other way is trying to maybe test it, just have some code that like a local, I don't know, distributed systems simulation trying to detect metastable failures, or maybe there's a way to create a logic system or programming language that prevents these kinds of failures. But the second version, well, both versions to me seem really, really hard. On the one hand, you have you need like a huge setup for your production instances, and like trying to dial over parts of the requests. Or on the other hand, you need to have, or it seems really hard to create such a programming language or create such test environments, given the example in 2.4, which actually fascinated me, since it's like dependent on both super low level implementation details as well as how the higher level database and clusters worked. So I wonder what your thoughts are.
Yeah, I don't know if because these are black swan events, right? And especially tests, you can only test what you know about. So that makes it really difficult using sort of conventional means. You could probably model it in TLA plus or something, and then get a proof that it does nothing else, because some of these will depend on additional behaviors. But that also was going to depend on like your exact gateway you're using and like all of these other factors, right? So I don't think it's actually possible to completely avoid, but we can improve on the situation.
They mentioned somewhere that the types of systems they're talking about. Yeah, you have everything from network switches to like SD card, not SD card, SSDs, like IO throughput. Like there's just so many different layers, and you have to completely replicate that and make sure that whatever load testing tool isn't providing predictable load and all that kind of stuff. So seems very, very hard to test completely.
Yeah. But on the flip side, they did mention, and I think this is like one of the classic takeaways from all of this kind of thing, right? It's like we tend to run these systems in the vulnerable state, right? Because we get more throughput when it works. And maybe we just need to have more buffer in our resources, which is sort of the point of at smaller scales than Facebook, obviously, having auto scaling, things like that. And yeah, you can run away auto scaling, but still.
I thought it was interesting.
Sorry, go ahead.
Oh, I was just gonna say, I thought it was interesting that they were like, yeah, auto scaling usually works. Like, that's all.
They do say it usually works over a long enough time period, though, and that time period may be too long to like mask the failure before it gets worse.
Yep.
But building off of what Brooke and Philip were saying, yes, this stuff sounds very hard to test for and think about, but I think reading this paper where my mind keeps going is that state machine on the first page where they have the vulnerable state, the healthy state, and the metastable state. And I feel like so many of these failures are coming from the fact that the difference between those three states is implicit, and we're not thinking about the fact that our system can be in those states. So, and like Brooke just said, we're often running these systems in the vulnerable state intentionally for improved efficiency. So we don't necessarily want to stop doing that. But maybe what we should be doing is thinking more about where those boundaries are between the different states so we can understand what the interactions are if any of the caches or anything that we've built are going down and what effect that's going to have on our hidden capacity and our advertised capacity. And just bring all of those assumptions kind of to the forefront instead of leaving them implicit like they are now. Then with that information, one of the last lines in the paper is proving the absence of a particular metastable failure may be possible by modeling worst case behavior or an adversarial environment. So once we understand where those different states and those boundaries are and what components are leading to the boundaries being where they are, we can start asking really pointed questions about what's going to happen to the system if this cache goes down, or if this like cable stops having load distributed over it. Just all these systems we're putting in place, we can start thinking about what happens if they fail and if multiple of them fail and so on. And I don't think we can do that until we understand exactly what the system we have looks like.
Yeah, the pie in the sky vision I have for like dealing with this sort of thing is you've got like, I don't know, like typed infrastructure or something like that, where like you can say that like this server needs to handle this much load or whatever, and like you set up the type system such that like it guarantees that'll hold, and like you have modeling tools and stuff for doing that. Like one thing I didn't get around to doing, but was thinking about maybe attempting, although it looks like the model doesn't fit quite right, was using that thing I mentioned last month, the machinations, the like game mechanic modeling tool, to like try and model the first example, the like 300 query per second example. But it didn't quite fit, but something like that seems like a neat idea. And then the other thing that occurred to me as a more like that's the like pie in the sky version is like quick write up a thesis or 12. The like more practical thoughts were like, you could probably get away with having like not needing like a whole production scale system in order to test for these sorts of things. And you're still testing, so it's still going to be, you're like groping around in the dark of the giant state space or whatever. But by using like intentionally degraded links, like you throttle everything down, your caches are smaller or whatever, and you just artificially make everything like less capable. And in theory, that maybe makes it better. I'm not 100% sure, because there's probably a whole bunch of like weird bonus interactions when you start adding stuff like that. But it seems like
so I think, sorry,
a useful technique. Go ahead.
Yeah, I think we need to make a distinction here between, and this is right at the bottom of the conclusion, right, between the known failure states and the unknown failure states.
Yeah.
Because if we know there's mean time to failure on this SSD, and that could create load or triggers, all that stuff, we should totally test for that, right? Is there some way that we could find, and they're hoping to make systems that are robust to the unknown states as well, which would then fall outside of any typed modeling or anything else, right? Like it's literally testing, finding some ways to test our unknown unknowns. And so I don't think we can ever get like a complete picture, right?
And the other piece there is that we actually do want to run the systems in these vulnerable states. That's why we're adding caches and stuff in the first place. So preventing that is going to hamstring your efficiency. And I think what they're trying to do here is find a way to run systems in states like that in a way that allows you to predict how they may fail.
One of the other things, I think they mentioned it, about like the running in the stable state versus the vulnerable state, was one of the ways to improve that situation is to bring them closer, to make the stable state like bigger or reach further, and like the margin is like you don't need to push as far into the vulnerable state in order to get the efficiency you want, was also another way to avoid that a little bit, at least.
Yeah, totally. I think that's also like in the class of things that includes, auto scaling or, having some capacity you can spin up in these cases. When you notice, actually, it might be nice for us to have like tooling, active tooling, not static, dynamic tooling that says, hey, we're getting close to that limit that we know about. Like, let's throw some more power at this so that we come back down from that trigger, right?
I think they mention something along those lines. I don't remember exactly what page it's on, but they talk about how one of the most effective mitigations they found for dealing with this is to actually change their caching, scheduling, et cetera, policies when they get close to the limits of their advertised capacity. And I believe they say that they were able to start automatically applying those policies as the system changes, but I can't remember exactly where that was.
Hi folks. So my name is Clifford, tuning in from California, first time joining. I work at LinkedIn. I recently joined on the data and infrastructure side. So very excited to dive into these topics. On the testing of these distributed systems, one thing that came to mind, and maybe some folks have experience here or have colleagues that have experience with these type of things, is Netflix has like Chaos Monkey testing things in production. I'm also thinking about Jepsen. I have not used Jepsen before, which is a distributed systems testing tool. And then thirdly, lots of these big companies, LinkedIn included, Facebook, they have a lot of their infrastructure. They have on-premise infrastructure at scale. And interestingly, things like Terraform, Kubernetes, things that will allow you to set up production environments from scratch is still something that's not done at these places yet. But for folks who have Terraform, who can spin up environments from scratch, that might be something to consider, look into. I'm definitely getting into that space myself, but yeah, that's on the testing side.
Yeah, absolutely. Chaos Monkey is a really interesting one, I think, in particular, and throwing it at production, because it's like literally this is the system, right? You know, that we're trying to test, and it better stay up, or maybe we can do this at a time that it's not in the middle of a product launch or something, and to know that it'll stay up during those things. Totally. Interesting bringing up Terraform and sort of like the HashiCorp stuff. Did anybody see the postmortem from the Roblox outage last year? Which actually, now that I'm thinking about it, it might actually be like, as they break it down, they're like, "Oh, it must be this." No, it's not that. It must be this. And they take the whole system down, clear the caches, bring it back up, and they like can't dial into the system. They can't actually get it running, like, you know, all of this stuff, and keeps going down. And I can't remember, I think it was like they changed the database or something like that was the reason that it kept going down. But it's not that the system would crash, it was that it had these infinite work queues, and could never actually get through the work. And I actually think, now that I'm thinking back to that, I think they actually did have some work amplification too. So it's like really subtle things. Even when you have these really expert teams working on it, you can still end up in a bad state from like things that don't seem related, right? So it's like really hard to model.
Yeah, now that I think about it, I think that Roblox case probably would fall into this whole metastable class of errors. They in the paper actually mentioned that like dealing with these problems, in the best case scenario, you do so using global information. Actually, on the page you have open, it's at the bottom of that paragraph. The best decisions are made using global information, but the communication required to distribute information can have its own sustaining effect. And thinking about that quote, I think that also applies to the humans working on the systems. A couple of the examples in here were failures across like 4 or 5 different components across the stack, where no individual engineer had all of the information needed to address these problems. And they were, in a way, their own distributed system, trying to fix these distributed systems that were failing underneath them.
Hi, I'm Casey, calling in from New York. One thing related to this sort of human part of failure in these systems, a lot of these work amplification issues, it feels like some of the things come around because they are built on top of things that are made for efficiency that are givens now. They're givens. Having a cache is a given. Doing a retry request is a given. And so I can imagine, not because they're things that aren't discussed, like why should we do this? The imagination it would take to go, hey, maybe one of these is the problem, it's probably a lot larger than, oh no, it must be the new thing we just added. Because the new thing we just added is the thing that's untried, when it's these like tried and true methods of making the system more efficient that can be the thing that's throwing this off. I found that fascinating.
I think
Yeah,
that's
it's
really
definitely-
good. Sorry, go ahead.
Mic drop.
Neat to see, or to think about the all of the sort of unexamined assumptions that come up and are likely to cause these sorts of things. And even if you do end up eventually with typed infrastructure or something, there's probably still going to be just inherently in the type system, that's going to be encoding assumptions as well. Seems tricky to get around.
Yeah, the one thing I like about it is you could add those constraints together. So if you modeled literally the specific SSD and knew the mean time for failure and all of these factors, you could have in this glorious future, right? you could have a library that lets you snap these components together and check things about them, or have like a SMT solver or something, right?
Yeah, that was definitely, I failed to mention it, but it was sitting there in the back of my head. Like the other component of the pie in the sky future is like, with all of your hardware, you get like a specification. Like we guarantee that it has these particular properties and these sorts of failure modes. And then like, as you are assembling your data center or whatever, or buying your hardware from AWS, like it'll like you'll be able to like specify specifically from the big database of like performance characteristics for specific hardware.
Cool. So who's starting that startup? Because I would buy from them.
I think
would
we'd
say-
still need to build the typed infrastructure system to start with.
Have you guys looked at test grounds, the IPFS test grounds? I used it for trying to ensure, I used it on a very, very small scale, like not the way it was intended, to ensure that two peers were communicating in an expected way. And they try to get around this. The idea is like, they do some like Kubernetes fun, or like containerized things to get nodes, and then you specify like, hey, let's make the network latency this, and let's, it's not to this scale, but there was an attempt. There is an attempt at this, if anyone's interested in looking at that kind of thing.
Yeah, and I dropped a link in chat, and that looks really cool. I haven't seen that. I liked what you were saying a couple minutes ago about how caches and stuff are taken as a given. Even outside of the context of distributed systems, if I run into a regression, the first thing I do is look at like the most recent couple of commits that may have introduced that regression. And then sometimes if the bug comes from something that's like a commit 2 years ago, that's just always completely out of left field. It takes forever to find, and it's definitely not the first place I'm going to look. And so I think that that's a really good insight about these problems, because they're like infrastructure bugs, which are hard enough to find on their own, but distributed over both time and space in a way that just makes them kind of nightmarish.
I always assume it's my last commit. That's the problem.
So do I.
Yeah.
Yours, I mean.
Oh, yeah.
It's a good heuristic.
Yeah. You figured that out quickly, huh?
I'm kidding.
I had a comment about Na's idea of a typed infrastructure. I do think that even if you end up like specifying very deep down to the lowest level what hardware you run on, what everything in the stack is, on the one hand, I think it's going to be really hard to capture all of the specifics in types. I mean, and I guess that might be one problem, but you could, in theory, test everything you specify in your types against the actual system and maybe get really confident that it actually matches. But I think the other big problem is, will you be able to abstract? Like when you run something on AWS, there's hypervisors in between. There's possibly different hardware underneath. And that's all possible because it's all abstracted over what it's actually running on. But if you want to capture all of that in your types, is that even possible, right? Or is it even desirable? Don't you want to be abstract over what you're running on?
Yeah. So you're right. We would have to capture like really granular detail to get that level of understanding. It might be enough to get a sense of where the edges are, but you're right. It's like, well, if there's a problem in your gateway protocol, then the whole thing's going to go down, or whatever it is. Actually, we're using types fairly loosely here. This is wow, this is way off topic, but this is probably not captured in statics. It's probably a dynamics problem, and so we would probably want to capture this this information, right? Not as static information, but as like a curve over the inputs or the running system.
I think the paper actually addresses your point a little bit, Philip. First, they define characteristic metrics, which those end up being the things like number of page faults, cache hit rate, the thread counts, and so on. But then later on, they say that when you're trying to model systems like this, instead of aiming for perfect fidelity, they think that what you should be doing is controlling the test environment so that the characteristic metrics of the test environment match the full scale environment. So you're not trying to match the specifications of the hardware or anything like that precisely. You're trying to figure out which metrics and characteristics of the hardware are relevant to these failures so you can model those. And I think that that's a much more tractable problem. Still not an easy problem, but you're not trying to simulate the universe inside of your computer, at least.
Like let's simulate cosmic ray events.
I'm sure
So I
there's
guess-
places that do that, and I'm glad I'm not working there.
I mean,
So I guess
simulating.
the idea, sorry.
Go ahead.
So I guess the idea would be like, instead of trying to capture what the actual hardware is going to do, you have lots and lots and lots of dials of failure rates and
Exactly.
performances, and you'll see you have some really, really hard to figure out graph of like how everything like influences each other, and then we'll know if there's this set of parameters which are at a certain level which is somewhat real world like, or might happen in an actual system, then you know you'll have a metastable failure. Sounds at least possible. So yeah, that sounds interesting.
Yeah, exactly like that. I think you see this a little bit in things like TLA plus when people are modeling like queues, for example. They're not modeling like the internals of the queue and how the queue pulls a job off of the queue and processes it and emits an event. They're modeling like the rate of incoming work, the amount of time it takes to process a piece of work, and the percentage of time that a job fails. Those are very high level and abstract dials that you can tune to see how the system changes as you modify them. And I suspect that they're getting more at that sort of idea than they are trying to implement Kafka in like linear temporal logic.
I guess you'll never be able to find issues like described in, like it's still I'm mentally still coming back to the 2.4 section 2.4 issue.
Is that the link one?
Yeah, the link one. And I think even like if you're doing that, then you're doing exactly what let's say the engineers from the, I think, database team or something were doing, where they were abstracting about what's underneath, but the problem was actually in the concrete application or the concrete stuff that they're using underneath, and how it connects to what's above. So I guess it may not be able to find such problems, but yeah, I don't know.
With 2.4 though, there is an implicit assumption that they're working with though, which is that all of the work is going to be evenly distributed across all the different links. And they took that as a given, but by modeling the right characteristics, maybe they would at least be pushed towards thinking about the possibility that that assumption may not be accurate, even if the system isn't going to tell them exactly how that failure can happen. I think with a lot of these failures, it's less about having the computer tell you exactly what can go wrong than it is having the computer guide your thinking in the direction of the failures.
And maybe that's the really useful part, is knowing those things, and then when this happens, being able to identify it and fix it, as opposed to just straight up preventing it, because again, some of these may be black swans.
Since you mentioned it, Quinn, one of basically the first thought I had when I saw the mention of characteristic metrics was Goodhart's law. When a measure becomes a target, it ceases to become a measure. And that seems like that's going to be an issue if that is the strategy adopted as the one going forward, because then everyone will start optimizing all of the commonly noticed characteristic metrics, and then there will be an entirely new set that no one noticed until they started getting new metastable failures. And it seems like you're doomed to whack-a-mole if you take that approach alone.
I agree. They actually address this too. In section 3 under organizational incentives, they talk about how if you have like kind of like first order incentives, like minimizing the cache eviction rate, organizations will optimize for those, which will cause these sorts of metastable failures. But if you move up a layer and instead optimize for recovery from cache loss, then that metric is going to encompass all of the possible failures that lead to cache loss and the failures that result from them in the first place. So yeah, I think you're absolutely right. The Goodhart's law applies here, but that I think part of the lesson there is to be really careful about the metrics that you're choosing and ensuring that they actually reflect the whole like class of failures that you're trying to prevent instead of just the instances that you're aware of. And I know that that probably sounds a little bit like a cop-out because you don't know what you're trying to prevent, which is kind of the whole point of all this. But yeah, I understand what you're saying.
On the on section 4, when they say, can you predict the next one of these metastable failures rather than explain the last one? At a high level, I was thinking like, okay, how can there be a grassroots movement like, from the engineer level that just percolates, and then a culture is created of like, solving this wider issue. So what I was thinking of, and I don't remember where I read this a few years ago, could have been Facebook, might have been Facebook, where they had a day. It was part of their culture. I don't remember the company, but they would like throttle network requests. I'm thinking about the front end and UI, how you can throttle your Chrome developer tools. Other concepts that come to mind are like frugal innovation, trying to do the most with the least amount of like hardware you have. Like, I think it was implemented kind of like, a few days out of the month, you're going to run your systems like this because there's actually real people in other continents of the world that use limited hardware, software, RAM. So get used to it, basically. And don't forget that not everybody has an iPhone or what have you, high compute device. So yeah, that's just a high level idea of like, how could everybody kind of pick up this spidey sense that could perhaps over the long term help minimize these type of failures?
This isn't really my domain, so I don't know if this is something that happens, but something that I've seen quite a lot within the cybersecurity space is this idea of embedded security champions, where rather than having one like ivory tower security team that oversees all the other teams and tells them what to do, you kind of have these individual champions that rotate among different teams, embedding in them for weeks or months at a time, and working with those developers to help them think about things from a security first perspective, ask them hard questions about their code, document their answers, really just try to make all of their security assumptions explicit. And I could really imagine, I'm sure someone is doing this somewhere, but I could really imagine something like this working from like an SRE perspective, where you literally have SREs with expertise like this jumping on to like an internal tools team and just really drilling into how these systems work and what assumptions they're making.
I thought that was maybe kind of part of the idea of DevOps, possibly, but I never really looked into the whole overarching concept. So maybe I misunderstood. But it seems like that's at least part of it, is the like you want your developer and ops stuff like intertwined so that they can both see like what the other is doing and can see the pitfalls they might fall into, like not being aware of them.
I think it's part of it for sure. One of the big things that you get with like the security champion idea is that they are rotating throughout the organization. So they get a view into how a lot of different teams are working and are able to start spreading knowledge between them. And when they come into a new team, they're looking at their systems with a fresh eye. So they're not taking anything for granted about those systems, and they're able to point out anything that looks a little bit weird. At least my own experience with DevOps is that usually the DevOps person is a member of the team that they're working with. And so it's more so them working on the systems that they have built and grown over the years rather than almost like auditing like the DevOps posture for that team.
Okay, yeah, that
I don't know if
is
that's the case
definitely a big
everywhere.
difference.
That's just my own experience around it, but
That makes sense, and I can definitely see how having like all I can think of is like bumblebees pollinating all the teams with like cross-pollinating the different knowledge or whatever.
I like that.
It
So
definitely
what
makes
I'm
sense.
hearing is this all comes back down to humans working together and communication, as it always
Oh,
does.
Always.
that was actually one of the things that I was thinking about a bunch reading this paper was like trying to find or thinking of like failures like this that weren't quite conventional. So like I linked it in the Discord. One of the first things I thought of was there's a video that was published somewhat recently about the 2003 blackout in like southeastern Canada and the eastern United States. And like that seemed, it wasn't quite the same because it was more of a cascading failure than a full like metastable situation entirely, maybe, but it seemed like it rhymed at the very least. And like the other thing that occurred to me was you could like it seems like you could have like metastable failures in things that are entirely non-technological. So the like the example that occurred to me was like something new, some physical product is released and it's like in short supply for some arbitrary reason, like maybe one of the ships sank or whatever, and so there's just a bunch missing. But because of human nature, it's like it's a low supply item, and so people want it more, and like it becomes a prestige item, and now it starts selling out because like everyone's buying them all up, and like that builds a feedback loop in the same sort of way, but it's entirely a social system, or probably slightly more applicable to the sorts of things this paper was thinking about. It seems like user behavior is probably something worth thinking about. So like if everyone starts like hitting F5 when everything gets slower, like now the users are doing the work amplification for you. You don't even need to like accidentally your cache.
So we need to model the users in the system too. Great. Yeah, I really liked the, so for those who haven't seen it, it's in the Fission Discord. I really liked the traffic video as well, because like there's lots of paradoxical stuff that happens there. You increase the size of, the width of the lanes and traffic slows down, right? Like all kinds of stuff like this. That's absolute like, and like a direct parallel, because we're, we can think of these as, links, right? Yeah. So yeah, super interesting thinking about it in other areas. So we're essentially at time. So anybody have wrap up thoughts, and then we can talk about next week and further session.
Not related to the paper, but I haven't read a research paper in a good year, and getting back into this is very exciting to me.
It's good to have you here. I really liked all the thoughts you were jumping in with, and papers are great. People should read papers. I thought this was a really a good paper for this topic. It was super approachable and just had my mind racing the entire time I was going through it.
What I liked about, so one thing that I really liked about the paper and about this discussion also is it really feels, because there were so many questions that came out of the paper was like based, the whole point of the paper was to define terms so we could ask questions. I liked that it sort of admits that we're in the infancy of understanding some of these things. And although I applaud the idea of, hey, let's figure out a way to know the unknowns before they happen. It really feels at a practical level, we're just going to be hitting those for like a while before we can even come up with a class of things that we don't know. But I appreciate that everything was about this question, so it lays the groundwork for being like, hey, this is the goal. But then I feel like at a practical level, we're just going to be hitting those. We're going to just be reading papers about various black swan events for X amount of years before we're able to really like understand what's happening.
Yeah, this is like 2021, I think. Like this is cutting edge.
Yeah, this was definitely a 2021 paper.
To follow up what Casey said, I think the infrastructure as code movement, as more organizations try to basically code up their infrastructure so it's just easier to just mentally think about and these things. I think this hopefully it's gonna kind of help move this area of research forward and make it more practical, I hope.
Amazing. That's maybe a good thought to end on, that we are still figuring all this stuff out. None of this works, and good on the authors for essentially writing a paper saying, we don't know what's going on. Does anybody else? So awesome. So next session is in a month. I don't know about anybody else, but the month in between felt like really long. So we might, if anybody else is feeling that way, drop it in the Discord. We can do these more frequently if that's helpful. Next month, unless somebody has another paper that they want to look at, we have a certain tendency of the database community, which is the snarkiest title I've read in a long time. And then after that, we have no papers scheduled. So I thought I would kick it off by just picking 3 off the top of my head and be like, I don't know, these ones. If anybody wants to suggest papers, very open to that. I can keep filling this queue up, but you'll get really like the things I happen to be reading, right? So I would really like other people to suggest papers, even if you haven't read it, like, this one sounds interesting, and we can go through it together. Yeah, thanks everyone for coming. The recording will be available shortly. Zoom always has to take a little bit of time processing it, but I'll post that and send that out to everybody. And thanks everyone for showing up. Thanks for all the newcomers. I mean, we've only had one session prior to this, but thanks for everybody else who came, and see you all next month.
Yeah, have a nice month, everyone.